Hello, my name is Seth Temple. I am a second-year statistics PhD student at the University of Washington. Today I will be presenting my research preliminary exam report, which is based on this paper by Stockdale, Kiprios, and O'Neill. It's a biostatistics paper from 2019, pair-based likelihood approximations for stochastic epidemic models. I'm going to jump right in as we start to describe modeling epidemics. Epidemiologists are generally hoping for flexible and general models to describe the incidence, spread, and control of contagions that threaten human, animal, and plant welfare. With these statistical models, we're able to ask important questions. For example, how do mitigation efforts affect disease spread? Or how do diseases spread between subpopulations? Today, to frame the problem, we'll be actually talking about this epidemic process being partially observed. So I will have removal times, where removal could mean that an individual is no longer infected, whether that's due to a quarantine, death, or a diagnosis. And so these will be the times that we observe, denoted with R. What we don't observe is the infection times, denoted by I, when the individuals are initially infected and contagious. Now, these analyses with partial data will be done either by integrating over the missing I's or by augmenting the missing I's within a Bayesian framework. If we're willing to take independence between pairs of individuals, we will arrive at likelihood approximations that are both fast and within the frequentist paradigm. As a starter, I'm going to describe with a little cartoon animation the stochastic epidemic model. So here in blue, I'm going to have infection rates beta kj that vary between individuals. We'll have removals such that the infected individual has an infectious period, rj minus ij, that will be gamma distributed with an integer shape parameter mj and a removal rate gamma j. Throughout, I'll try to use the time variables in the orange font, and then in a purple font, I'll have the removal rates. This first picture is describing alpha, a patient 0, that is trying to infect the initially susceptible population. Now, at any given time point, we'll have counts for the susceptibles, the infecteds, and removes. And these should always add up to a fixed total population size, capital N. So this cartoon here is the main picture that you should keep in mind. It's our canonical cartoon. So in yellow, we have the susceptibles. In orange, we have the infected. And in green, we have the removes. I'm denoting here with gray arrows that we cannot infect an initially removed or someone that's already removed. And then in the orange arrows, we have that the infected individuals are trying to infect the susceptibles. And with beta kj and beta kl here, I'm suggesting that we could model with different infection rates between individuals. The epidemic will end for this SEM when there are no longer infected. At that time point, we'll know a new variable, little n, which is the epidemic size for the total number of infected. We can simulate such an epidemic by exploiting Poisson processes. I will introduce an algorithm to do such. One, because it will introduce a key idea for our theoretical developments later. Two, this is the algorithm I will use for a simulation study later in this talk. So this algorithm, my epidemic simulator, will be using the idea of a race or an exponential race, which is the minimum of exponential random variables. Within the algorithm, we have an initialization step, and then we enter into a while loop, the while loop being until the epidemic ceases. And the key idea in this while loop is that we are going to be racing Poisson processes. So we'll have S of t, I of t Poisson processes with a common rate beta. These correspond to infections. And then we'll have I of t Poisson processes with the removal rate gamma. These correspond with removals. And we will see which Poisson process between these competing adversarial Poisson processes wins the exponential race. The time in which that winning case happens will be T1. And then we'll update the counts I, R, and S according to if it was a removal process that won or an infection process that won. Now this stochastic epidemic model can be understood as a bivariate continuous time Markov chain or a Markov jump process with the transition probabilities or jumps being based on an underlying Poisson process. A key quantity here, a time quantity in orange, will be tau kj. This is the time that the kth individual tries to infect J. Next, I'll introduce some shorthand probability statements. So we have psi j. This is the probability that J is not infected before infection time ij. And if we look at this form of the exponential function and recall properties of exponential, we can look and see a psi kj, a marginal term for the before infection probabilities. Throughout, I'll be using in violet these before infection probabilities psi. These will be important as we'll try and approximate these values. Next, we have chi j. This is sort of the instantaneous probability that J is infected at time ij. And this is, in fact, the jump probability from this CTMC. Next, we have phi j. And this is the probability that J doesn't infect the never infected, of which there are capital N minus little n never infected. Lastly, I'll say that the psi and phi terms can be understood as survival probabilities with respect to the CTMC. Now, if we actually had the infection times, we could write down an explicit model likelihood with these shorthand probability statements. This is what's shown here in Formula 1. So we're writing down what I refer to as the augmented model likelihood, where we essentially have for each infected individual, J, we have their before infection probability, their jump probability, the probability they don't infect the never infected, and then they're removed with some density for their infectious period length. And then lastly, for patient 0, which for simplicity, I'm just calling the first individual, we're not going to study how patient 0 became infected. This is why we don't see psi and chi terms here. Now with Formula 1, maximum likelihood estimation is easy. We'll just take a log, take a derivative, set equal to 0. And this is for, say, a common infection rate beta and removal rate gamma. Here are those explicit values. And this is with the complete data where we have infection times. Now, in practice, we don't have infection times. So how a Bayesian would do this is with data augmented Monte Carlo metropolis Hastings. So here we construct a metropolis within Gibbs sampling routine. And for simplicity, I'll assume common infection rate and common parameters for the infectious periods. First, we have Gibbs steps for beta and gamma. This is assuming some conjugate priors, such that we still have draws from a gamma. Within this procedure, we'll have to estimate, or not estimate, calculate these values A sub I and C sub I, which here I'm trying to really emphasize with the color font and with the subscript I that these depend on the infection times that we're augmenting. And then we have a metropolis Hastings step with some nice proposal density F to update the infection times I. Now the scheme will suffer from high posterior correlations. Again, I'm trying to emphasize this with the color font for A and C to say that these terms are principally important in our Gibbs steps. Now we can either fix this issue, this is sort of the body of work in Kyprios in his thesis, or we can evade it entirely. And evading this entirely is the focus of this research. So here, Stockdale, Kyprios, and O'Neill derive the partial data likelihood. So first, they'll integrate over the missing infection time. Next, we take a convenient change of variable. And the idea behind this change of variable is to absorb info on the never infected into the density, such that we have a new density, GJ. Now, here we have a nice permanence of these new densities, GJ, such that they're still gamma distributed. And we have the same shape parameter, MJ, with a new rate, delta J. And here I'm describing what delta J is. It's essentially the removal rate plus some information from the never infected. And then I'll say that this function A is really a moment generating function for the infectious period length. So next, we have the partial data likelihood. Again, we integrated, we did a change of variable. And here we have formula 2. And in violet, I'm trying to emphasize that the rest of this talk, we will be trying to approximate this expected product of these psi-chi terms that we still have remaining. So how do we approximate that expected product? So there's two ways in this work. So formula 3 is saying, okay, let's assume that an expected product is the product of expecteds. Here we'll assume that we can model the before infection probabilities, the size, independently of the jump probabilities, the chi's. Next, 4, we will take a similar strategy. So we'll say expected product equals product of expecteds for the chi terms. But we won't simplify for the before infection probability psi j, keeping them as an expected product. Now, if we start to write this explicitly, and if we assume a common infection rate, beta, between pairs of individuals, we end up observing this orange term here, which is a double summation over tau terms. Here I'm calling this W, which will be the cumulative time that infected try to infect susceptibles. Now, if we look at this form, we see that we have a moment generating function of W at negative beta over n. So this paper will present multiple likelihood approximations. Here it's a likelihood approximation because we've taken these assumed expected product equals product of expected. So the first one will go even further. We're going to assume marginal pairwise independence of the before infection probabilities, the psi terms. So that's what I'm showing here with the violet terms. We knew that psi had a marginal interpretation. So we'll say expected product equals product of expected. And here we refer to this as the standard pair-based likelihood approximation because it's rather general, can be used for a variety of models, and it seems to perform well in simulation studies. Now, the original paper shows two similarly derived PBLAs, which I discuss in my report. So next, the first theoretical development, lemma 1, is saying how do we get these pairwise expectations? And we can get some explicit formulas here. So if we look at this past page, we have this expected marginal before infection probability term we need, and then we need an expectation of that with an indicator as well. So that's the work of formula 6 and 7 in lemma 1. And we can actually get explicit formulas here that we could codify in a software program. So I want to go over a little bit of the proof strategy here. So as a sketch, let's focus on these terms tau kj, which is the time that k tries to infect j. And we can actually partition tau. If we think carefully about these tau quantities, it really only has 3 cases. And you can essentially draw a number line and identify what these 3 cases are. And so we can partition according to these cases, which is what we're doing here in 8. We partition such that we have the sum of 3 expected values. So we can evaluate these terms in formula 8 separately. Here, solving double integrals is certainly possible. However, we're going to want to extend this to, say, gamma infectious periods. This result is for exponential infectious periods. So we'll want to extend this. It's going to be helpful to think about this in the context of Poisson processes and make a probabilistic argument. So as a sketch of this probabilistic argument, since we're going to study various cases, let's just assume for illustration that the removal time Rk is less than Rj. So we're going to be traversing the CTMC process backwards from the removal time Rj. So between this interval Rk to Rj, we only have this delta J Poisson process, so this jth Poisson process. Now we have a probability for no renewal in this interval for the delta J Poisson process. Now, if there's a renewal, but we know that this renewal is infection time ij because the case process hasn't started. Then at time Rk, we'll begin the delta K Poisson process. Now, if we haven't achieved a renewal from the jth process, we now have a compound Poisson process with delta J plus delta K rate. And for this compound Poisson process, this superposition, we have an exponential race with probabilities for the renewals of the jth and kth process being shown here. We can also set up these exponential races with, say, a beta Poisson process. And essentially setting up these exponential races is how we'll derive various probabilistic arguments. And with these probabilistic arguments, we arrive at expressions for the terms in formula 8. This strategy can be extended to Erlang infectious periods. These are gamma infectious periods with integer shape. And here it just needs to justify a combinatorial extension. So here I introduce the language of, say, a full renewal, where a full renewal for this Erlang infectious period occurs after, say, mj or mk marginal renewals of these Poisson processes. The combinatorics here say, okay, between the interval Rk and Rj, we can have, say, mj minus p minus 1 marginal renewals. Then when we hit Rk, we have this superimposed process, and we're going to have a bunch of exponential races, L plus P exponential races, where the jth Poisson process wins P times. Then we know there's another Poisson process race where the jth process wins at time infection time ij. And then we complete out the argument for the kth Poisson process. So working through these combinatorics is essentially how we get a rather nasty expression for Erlang infectious periods. Now, these schematics can be described a lot more clearly in Jessica Stockdale's thesis. Next, lemma 2. This is how we arrive at an expression for formula 4, which was one of our other types of likelihood approximations. So one thing I want to highlight here in lemma 2 is that here we're now having constant delta rate. And if we recall from some previous slides what the delta rate was, this really implies that we have a common infection rate beta between individuals, and we have a common removal rate for all individuals. So here, this is a limitation I would highlight. And then this result is essentially saying if we have some double summation over tau terms, can we arrive at an exact distributional result, which we can. Here where this double summation of the tau terms is really a summation of scaled exponential random variables. And the idea of this proof is to traverse this process in reverse again and make a convenient change of variable. These ideas being the main strategies we take here. Now, if we consider this subset script K to be all of the infecteds, well, we've arrived at W, which was the cumulative time that infecteds try to infect susceptibles. So with this exact distributional result, we can arrive at the moment generating function at negative beta over n. As a recap for these methods, Stockdale, Kiprios, and O'Neill propose, in fact, 6 pair-based likelihood approximations, 2 of which I have highlighted here. This makes maximum likelihood estimation possible despite the partially observed data. With the sketch of the proofs, I've really emphasized how we use properties of Poisson processes. The main idea here in these likelihood approximations is that we can say the expected product is approximately the product of expected. And since these are pair-based methods where we're studying the pairwise interactions between individuals over the course of an epidemic, this is really an O of n squared task, computational task. Okay, next I will be speaking about some simulation studies. And for all of these simulation studies, I am using the algorithm on slide 6 with inputted values for beta, gamma, and capital N, the population size. So I wanted to do some additional simulation studies on top of the ones that Stockdale et al. Do in 2019. So first, how fast are these likelihood approximations? That's sort of describe the behavior of these methods and the maximum likelihood estimates that they arrive at. So when is this pairwise independence assumption that is really the assumption of saying expected product equals product of expected? When is this inappropriate? And then does pair-based likelihood approximation inference offer consistent estimators? I also did a little bit of work studying underreporting and how that impacts inference here. In general, if you have undercounts, this is going to result in a lower estimate of the basic reproduction number. So for my study of the runtime comparisons, I increased the number of infected n and recorded the time in seconds that it took to compute a single likelihood. And for, say, a standard Newton-Raphson type method in R to find a maximum likelihood estimate, you might have to compute this likelihood multiple times. So here, having this fast computation of the likelihood is very important. So here I'm comparing the standard and then the product methods, the 2 that I've highlighted so far. There's also sort of a normal approximation that is akin to the product method. And then I'm also comparing to what's called the Eichner-Dietz approximation in Stockdale et al. And this is really a numerical integration technique for the nasty integral of the partial data likelihood. So it's no surprise that the Eichner plus Dietz method, where we do numerical integration, is not fast at all and doesn't scale well as the epidemic size grows. Now, the product and the weak limit methods are very similar. This is because though we've maybe sped up the computational task for evaluating the before infection probability psi, we still have the O of n squared calculation for the chi terms. So these calculations are still quadratic in nature. And then the standard product-based likelihood approximation, the more general method, seems to be about 5 times slower, is what I'm seeming to observe in this table. Next, I sort of studied how these methods deteriorate as we have more people infected. And that's what's being shown here. So here I did 2,000 simulated epidemics with a common infection rate and a common removal rate. And I'm not showing the plots for the MLE estimates of the removal rate because it's very similar. And then I subset according to the infected proportion to get these various deciles. And I'm comparing between the standard product and weak likelihood approximations. And since they're approximating the same likelihood, we should expect that they arrive at the same maximum likelihood estimation, which they do for epidemics with less people infected. But as more people become infected, the various independence assumptions that these methods take start to arrive at different results, which is what we're starting to see when we get to say 50%. Standard and product and the weak are definitely starting to diverge from each other, and it gets just worse and worse as the infected proportion grows. Now here, a big concern here, which Stockdale suggests in their supplement, is that as more and more people are infected, we have more of these before infection terms, the size, and these are actually the terms that we're aggressively approximating the most. And this is perhaps a justification for why when we have more people infected, we're doing more and more approximation that's possibly not justified, and we're arriving at worse and worse results. Next, I thought I would compare against the complete data. So these methods, the likelihood approximations, are really partial data methods. And I'm comparing against the complete data to see and assess the consistency of our maximum likelihood estimates. So this plot is for R naught, the basic reproduction number, which in the simple epidemic model is beta over gamma. And as the infected proportion grows, well, we have more data. So we're getting more centered and focused about the true R naught value as these purple gradients get more and more purple. Now we see a rather strange behavior when we do this subset by the deciles of infected proportion for the standard product-based likelihood approximation. Namely, we see as the purple gradients for the infected proportion grow, our estimates for R naught also grow. Now this is quite concerning because we want to see that we're getting an estimate of R naught, which is the true R naught, which is the simulated truth, as 1.5, but we're all over the board depending on how many people are infected. And just another plot to talk about here, when we look at, say, the inference of the removal rate based on the complete versus partial data, so Stockdale et al. in their supplement suggests, oh, it seems like we're centering about the true value, the simulated value, that's good. But when we look at the actual complete data, which we have since we simulated it, the complete data is much more focused around the true value, as opposed to the partial data method. It's very diffuse. Now, during my actual exam, my oral exam, the comment was, well, it's no surprise that the complete data is better. The complete data has more data. And I definitely agree. I think my comment here is really, what is it that we can really hope to observe about the partial epidemic? Now, if you think about it, you really should have two columns or two rows, one for infection times, one for removal times. But if you are missing a column or row, the infection time column entirely, how are you hoping to learn too much about the transmission dynamics when you know there are these adversarial dynamics with the infection rate beta and the removal rate gamma? So we end up just with a rather diffuse estimate for gamma, which I'll discuss a little later. So here in the simulation study, I've suggested that the infected proportion n over n seems to calibrate our estimate for the basic reproduction number. And I think this may be related to a theorem from branching approximations from Anderson, Britain, 2012. Next, our estimates for beta and gamma with the partial SEM methods don't seem to estimate the true beta and gamma. And in fact, even when I fix the true values in simulation studies, I'm still not getting a consistent estimate of the other value. My conclusion being that the partial data appears inadequate for inferring these adversarial dynamics of infection and removal processes. Finally, I did some real data analyses. The one that I'll highlight here is an Ebola virus epidemic in West Africa with somewhat large numbers of infected. But I also studied a dog rabies epidemic in Central African Republic, where I suspect some underreporting of cases, a common cold epidemic on a remote island in the Atlantic Ocean, where I demonstrate the ability to have multi-type epidemic models where we have infections that vary by, say, age groups. And then Stockdale, Cabrias, and O'Neill also studied the foot and mouth disease epidemic in the UK in 2001, where there was a rich set of covariates and the infection rates dependent on a spatial distance. I didn't have access to this data set, but you can refer to their original paper. So for the Ebola epidemic analysis, we're going to actually study an SEIR compartmental model where the E stands for exposed. And how we're able to add in this model flexibility and complexity is that we'll replace the removal time RJ with RJ minus C for a fixed exposed period, C equals 5.3 days. So we'll replace those values everywhere in our formulas. In this analysis, I also used a fixed removal rate, gamma. And I should say that these fixed values, C and gamma, are coming from a comparison study from Althaus 2014. Next, I will allow infection rate beta kj to depend on a time value. Now, in our modeling framework, it's really supposed to be between individual infection rates, and how we incorporate the time is with an expected midpoint time, TKJ. Finally, we're going to compare this to a Poisson model for counts with a deterministic ODE-based stochastic epidemic or SEIR model. And then here, I just have a nice picture of the three countries we'll study in West Africa: Guinea, Sierra Leone, and Liberia. Okay, so here I have a table where I'm showing the maximum likelihood estimation parameters for these SEIR model. So my method that I implemented exactly matches those of Stockdale et al. In their original paper. So that's the PBLA method. And then Althaus is this Poisson model with the deterministic ODE-based fit. So we observe that we get similar values for beta 0, this null infection rate, and for K0, which is a time decay rate. And these imply similar basic reproduction number values. In conclusion, Stockdale et al. In their 2019 biostatistics paper have proposed likelihood approximations that make maximum likelihood estimation possible for the partially observed epidemic. And their methods are faster than existing methods, namely these data augmented Bayesian methods. They have promoted a flexible framework for epidemiology. How we do this is by specifying formulas for beta kj and gamma j, which I highlight with the Ebola virus epidemic analysis. And they show that this generally works in copious simulated and real data analysis examples. And then I found their work quite neat in how they've addressed this partially observed data without data augmentation, being deeply motivated by the transmission dynamics, which I have tried to highlight by relating their exponential racing ideas for the theoretical development to the exponential racing in my simulation for my simulator on slide 6. Some of my contributions, so I have written an R package, which is here, and I find it quite easy to modify in script. It's documented and it doesn't have any dependencies, it's all just base R. And I use this R package to reproduce all the simulation studies and data analyses. I also did some additional simulation studies, and the one that I really want to highlight is my observation that estimates from these partial SEM methods, which the pair-based likelihood approximation methods are, don't seem to be consistent for the simulated truth, that it's hard to infer both beta and gamma, these adversarial infection removal processes, when we don't observe anything about the infection times. And then I identified some corrections from the original paper. One thing to say is that these methods are scaling with little n, the epidemic size, the total number of infected, not with the population size. I also found that the Ebola analysis seems to take quite a bit longer than reported in the paper. And then I found some minor typos, which you can find in my report. Some future work, I think we definitely need to talk about what these partial SEM methods are actually estimating and the extent to which we can learn about epidemics with a lot of important data in this data stream not being observed and completely missing. So could we come up with another approach such that the partial observed SEM achieves consistency would be a question. I think it'd be neat to compare to, say, count-based models. So these methods are inherently individual-based. We have times in which individuals are removed or infected. Now, most epidemic data comes in as counts. For example, a study from Irons and Raftery, and then a recent study from Fincy, I think Wakefield, and Minin is also on this paper. So it'd be neat to compare and see, like, what more do we get when we have these individual time data, or does it suffice to just study these count-based models? And then, of course, we'd like to relax various model assumptions to have even more flexible and general epidemiological models. For example, we could set some of these infection rates, beta kj equal to 0. This would both result in faster computations, but also this framework is inherently a network in some sense. And you would think that some individuals are certainly not going to infect other individuals depending on some social networks. I started the study in a simulation study adjusting for underreporting. Of course, there's constantly underreporting in disease case monitoring. So that's something we want to analyze a little further and develop further. Then trying to study an epidemic in progress, what's referred to as online inference, is of principal importance. Now here, a deep problem that I've identified is that the partial SEM methods seem to calibrate their basic reproduction number values from the infected proportion. Now, in online inference, since the epidemic isn't over, we don't actually know the epidemic size yet. So it's going to be quite challenging here to develop these methods for epidemics in progress. And a similar story follows for demography, where people might immigrate or emigrate out of the population, or we might have births and deaths. Again, this is challenging because we then maybe don't know capital N, the susceptible population size, and we don't know little n, the epidemic size. Okay, so that is the end of my talk. Here I have a lot of the important references from this research. And at the end, I have a variety of appendices slides, which you can find on my GitHub. Thank you for your time and rapt attention.